Hi everyone. In this video, as I promised you, I'm going to talk about one of the most commonly used algorithms in optimization, especially for cases of nonlinear curve fitting like neural networks. This is the algorithm that used for optimization, and Levenberg and Marquardt are the name of the two people who developed this method. It is a smart method which is basically a mix of two well-known algorithms. One of them is the steepest or gradient descent that we saw in one of our first lectures, right? If you remember here, you move at each point in the negative gradient direction, which is the direction of the fastest or the steepest descent. The other algorithm is what we call Newton-Raphson method, which I have also mentioned in my numerical analysis playlist. If you go under numerical analysis playlist and look at the videos for finding the roots of nonlinear algebraic equations for one of the famous root finding algorithms is called Newton-Raphson. You can also use it to find a maximum or a minimum of a function. I'll show you. So this method is a mix of the two because each one of these methods have an each one of them has an advantage or advantages and some disadvantages. So this method tries to get the better of the two in each case. So we know the method of steepest descent or gradient descent, right? Which is, as I said, your next point is the current point minus some displacement along the negative gradient. And the amount of this displacement, if you remember, we call it the step size. If you have a function f, you can find the optimum step size. If not, then you have to do something about this step size, right? You have to change it because small means it takes some time, and being super conservative, fast means you might overshoot the optimum point along the line that you are searching, and it means more and more oscillations. Okay, so there is something that we have to do about this lambda in gradient descent. You might also hear the word vanilla gradient descent. Vanilla means the basic, the one that I told you in my previous lecture, okay? If there is no way to automatically adjust lambda, or there is no heuristic or no insight into how to change lambda and just go with the fixed number lambda, this basic equation is you might what we call basic or vanilla. So if you hear the word vanilla, you know what it means. Gradient descent or steepest descent, okay? So this is what we have. Now, what are the disadvantages of this steepest descent or gradient descent method that we need to improve on it? Well, the problem is this. I just mentioned it, but let me emphasize it. If a lambda is constant and you do not change it, what does it mean? Means when the function is in a flat area. So if the function you are trying to find the minimum of it or maximum of it has plateaus, has flat areas like this here. So you are here right now, you start here, that's your initial guess. And here it's quite flat, so the gradient is very small. And if lambda is constant, whatever it is, it means the whole step that you will take, this whole thing, is going to be a small number. So you are not going to move far, although you have to move fast to get out of this flat area and move toward the minimum, let's say. But you are going to take small step size and you get stuck basically on that flat area, okay? So that's the problem with flat areas. On the other hand, if there are sharp cliffs, steep cliffs, sharp drops all of a sudden, what you would do is this term is going to be huge, so you are going to take a large step size. And large step size means what? Means you do overshooting, you do oscillations, and still it might not do a great job. If you remember here, I guess I showed you the case that this method of steepest descent, the way it is also what we call a line search method. The way it is. What does it mean? It means this is the line of gradient, okay? This is the direction of gradient. And from your initial point, you move along this line, okay? Now, it's good that if you can exactly stop at point x1, which is the minimum value of the function you can have along this whole line. If you can stop right there, that's the perfect place to recalculate your gradient and basically maneuver and change your direction. But if you do a small step, you're going to end up here, which, as I said, it takes some time. If you do a large step, you might end up here, and here the value that the function has is bigger than this x1, so you're overshooting it. Again, when you go here on the next gradient line, you're not going to stop at x2, you're going to stop here. Okay, so you're going to have some oscillations, and that's the bad thing with this method, overshooting versus undershooting or small step size. On the other hand, the Newton-Raphson method can be used to find the minimum of the function, or in this case, the stationary point of the function. How? Well, in the video I mentioned under my playlist numerical analysis, you use this to find the solution of f equals 0, roots of function f. But here, I want to find the place where what? F is not 0, instead what? F prime is 0, right? Because stationary means what? Means the first derivative. If you remember, the first condition for a stationary point is the first derivative has to be 0, correct? So that's what we have here. We want the first derivative at point F to be 0, and that's what the Newton-Raphson method is using. What is this method is doing? This is what the method does. It says the first derivative, or in this case, the generalized first derivative, which is gradient, it says the gradient at the next value of x for function f is whatever it is at the current point plus the difference between these 2 points times the del 2, right, of f with respect to the x vector and higher order terms. Now, at the stationary point, if it's a single variable, we say f prime is 0. If it's the f is function of several variables, instead of f prime, we say what? We say del of f is equal to 0, right? So it depends on this scalar function f. This is a function of how many variables. If it's a single variable, we say f prime is 0. If it's a function of several variables, all of the partial derivatives, which are the components of this del, should be all equal to 0, right? So we say this guy here, I want, whatever I started, I'm hoping that the next point that I move to is the stationary point. So I want this thing to be equal to what? 0. And in the Newton-Raphson method, just like what we used for root finding, we try to neglect the higher order terms. Just consider the first term, which is a linear function of delta x. Now, here, if you do so and set this gradient of f at the next one equal to 0, you get your update equation. You take this del f to the left-hand side, becomes negative del f multiplied by inverse of this del squared, and then take xn to the other side, so you will get this update equation that you see here. This is the update equation of what method? Newton-Raphson method. It says if you keep updating your x according to this formula in the red box, it should take you from wherever you start toward the stationary point. Okay, now first and most important thing, what is this del squared, right? Again, if there is only one variable in f, that is corresponding to what? This is corresponding to f double prime, right? The second derivative. If f is a function of several variables, still this del squared, which we call the Hessian matrix, okay? We call it the Hessian matrix. This Hessian matrix still gonna be second derivative, but since f has so many variables in it, it is going to be a matrix, not a single second derivative. Every single term, if you look inside this matrix, is a what? Is a second derivative. But they are all partial second derivatives. And what are the components of this matrix? So if you look here, so this is the matrix of partial second derivatives. That's what it is, Hessian matrix. In the first row, all of them have x1 in them. All of them have what? x1, correct? So this first row is like what? Is like partial derivative with respect to x1 of what? The gradient, del of f. Correct? Remember, del of f itself is a partial of f with respect to x1, partial of f with respect to x2, all the way to partial of f with respect to xn. Here we assume we have n independent variables. That's the gradient of f. Now, if you take partial derivative of this gradient with respect to x1, so the first one is going to be second derivative of f with respect to x1 squared. Next one is going to be second derivative of f with respect to x1, x2, and then all the way to x1, xn. Correct? Similarly, the second row of that is what? Is the partial derivative of the gradient of f, but this time with respect to x2, and all the way the last row is the partial derivative of component of gradient, all with respect to x n. Okay, so all of them, each and every one of these n by n matrix is going to be a second derivative by the partial. And if your function f is continuous with respect to the variables, you can show that this matrix is a symmetric matrix. So this component here in orange is the same as this component in orange. Okay, because they are mirror image of each other with respect to the main diagonal. Or this guy here, let me use a different color. This guy here is the same as what? This one. So you're not going to calculate all n squared components. You just need to calculate what? N plus n squared minus n divided by 2, or n times n plus 1 divided by 2. You're not going to do all n squared minus n divided. So all the components you do is n again, which is n diagonals, plus n squared minus n, which is the off diagonal elements, divided by 2. This is the number of total thing you calculate. So that is going to be n squared negative n2. Yeah, that's right. So it's going to be n squared plus n divided by 2, while the total number of component is n squared. And clearly this is less than n squared. Okay? Unless n is 1, which is a scalar. So this is called the Hessian matrix, and this is what you need for the Newton-Raphson method. Not only that you need to calculate, you need to invert it. So once you have that information, the H matrix, the Hessian matrix, you can invert it. Negative of that times gradient added to xn is going to give you the next point. And this will lead you to the minimum of the function, right? Now, so first of all, this Newton-Raphson method is a very fast converging method if it is started in the right point. If your initial guess, as you watched hopefully my video under numerical analysis for root finding, you saw that the Newton-Raphson method is amazingly fast if the start point is close to the root. In this case, if the start point is close to the global minimum, then yes, you might have amazingly fast, we call it quadratic convergence, right? If that's the case. Why is that? Because this Newton method, not only it is caring about the gradient, it also cares about this Hessian. And what does Hessian give you? The gradient gives you the slope, correct? What about Hessian? Hessian gives you curvature. So here, not only you look into gradient or slope, you also try to benefit from the curvature information. And if you remember, second derivative in calculus is curvature. And look at all curvatures along all different directions and try to use them to guide you toward the goal point, and that extra piece of information will help you converge faster. For example, if you look at this simple kind of function, which looks like a something like x squared plus y squared, of course not exactly, And this picture is, by the way, from Wikipedia. If you look at it, the green one here is the gradient descent algorithm, while the red one is the Newton-Raphson or NR algorithm. And you clearly see that the Newton-Raphson takes a quite more straightforward path and it converges faster. Because gradient descent at each point tries to take a path that is in the gradient direction. If you look at the contour plot, the gradient is at each point perpendicular to the contour plot, right? So if I do it, at this point, if I draw a perpendicular to the contour, right, or here I draw a perpendicular, here I draw a perpendicular, here, and so on and so forth, right? If you look at the contour plot, the direction of gradient is perpendicular to the contour at that point. While here, you see that's not the case. It is using a mix of curvature and gradient, and so it is taking a shortcut and making it go faster, okay? Because it says, hey, if you move in this direction, the curvature is helping you get faster than just going based on the slope, right? And one of the places that it shows itself very well is when your function that you're trying to optimize has sharp cliffs. When you have sharp cliffs and the curvature of this sharp cliff in different direction is of course not the same, right? So let's say you have something like a narrow valley. Let me see if I can draw something like that for you. So, or let me not make it super sharp. Let's say something like this. Okay, so you have something like this, right? Now, if your optimizer is here, what's going to happen? The gradient is trying to look in the gradient direction and move, while this method says, hey, look at your curvature. In this direction is kind of flat. In this direction, you have a what? In this direction, you have a huge what? Curvature, or a very small radius of curvature. So it says instead of moving in this maybe slope direction, you better move only in the direction that has what? A huge curvature. So instead of going along this narrow valley, it takes you to get to the bottom of the valley very fast. Okay, so it stops you moving in the directions that you shouldn't be moving. If you see, this gradient has both a component parallel to the valley and one down the valley, but the curvature tried to fix it a little bit more toward going all the way down. Okay, so by looking at curvatures in different directions, the Newton method corrects or improves on the performance of the gradient descent. Now, I'll show you with MATLAB code a couple of examples, and you'll see that in general, Newton method can be way, way faster than gradient descent. Now, what's the problem with the Newton method? If it's such an amazing method, what's the problem? Well, several things. First of all, I mentioned one of the major disadvantages. The major disadvantage is this method is amazing in performance when what? When your start point is close to the goal point. Sometimes your start point is far away and can basically get into trap. It can easily get into traps. Traps of what? Let's take a look. So one of it is, I show you 1D cases, and you can again also look at my video on failure modes of the Newton method. So okay, so here is that video on my playlist. It's called Root Finding for Nonlinear Algebraic Equations, and this is the update equation of Newton-Raphson for root finding, not a stationary point. And you see there are several failure modes. One of them that we call getting trapped is this case here. that the method gets trapped in a local minima. So you start here at point A, and what this method does in 1D is basically draw a tangent line to the function wherever it hits the x-axis, project it back on the function, that's going to be your next point, and then keep going, and this method easily get trapped in the local minima instead of some global minima. The other is if the function has this kind of concave appearance, then if you start here at point I and keep following this method, it would actually diverge instead of converge. And it might here also see the case that it converges to some other roots. In our case, it might converge to some other minima, local minima. So this method has the disadvantage, it has failure modes, especially, as I said, if you don't start very close to the global minimum, which you have to be very lucky to do that all the time. But that's not the only thing that this method has disadvantage about. Another thing that this method has is basically the Hessian matrix itself, this guy. First of all, calculating this needs calculation of lots of partial derivatives. And if you don't have a function for f, you have to calculate all of these numerically using, let's say, finite difference. And not only you have to calculate all of those finite difference things, now worse than that, you have to invert it. And you know, inversion of a matrix, especially when the size of a matrix is large, is a very time-consuming operation. Okay, so when the dimensions go up, although this method can converge very fast, this Hessian matrix and the calculation of that could be a prohibitive factor, okay? And what else can go wrong? A couple of other things can go wrong about this Newton-Raphson. Let's talk about them. What if this matrix that you're trying to invert, this Hessian, is singular? You know, if a matrix is singular, in this case, since this is a square matrix, so all you need is determinant of that is 0. If the determinant of this Hessian is 0, so it's singular, you cannot invert it. The algorithm would fail, or this inverse is going to give you very, very huge step sizes. Okay, so singularity of the Hessian matrix is a failure mode for this algorithm. But not just that. If this Hessian matrix, which is an n by n, is not positive definite. What is positive definite? Please watch my video under linear algebra. There is a video that specifically I talked about positive, negative definite, positive semi-definite, and so on and so forth. Please watch that. And you can see a matrix is positive definite if the eigenvalues are positive. So if this matrix is not positive definite, maybe indefinite in this case, so some positive, some negative eigenvalues, then this method will not lead to the minimum. It makes you wander around. Really? Yes, I'll show you in a few minutes in a demo. But this method, the curvature can completely lead you in the wrong direction if this Hessian matrix is not positive definite. So that's another very important thing, a big limitation. If it's not positive definite, then the search direction will not lead into a descent direction. It does not send you down the valley. Remember, your goal here is to minimize the function. And if this is not positive definite, it will not lead to your optimizer go down. The other case I mentioned, if it's singular, then you cannot use it. I also mentioned for you, it can diverge, it can get trapped into a cycle in a local minima. The inversion and calculation and inversion of the Hessian matrix is time consuming, and you're really depending hugely on how close you are to the initial guess. So this method is amazing, but if everything lines up, okay, otherwise it can fail. On the other hand, this gradient descent is quite more robust, quite more reliable, but sometimes can be very slow. Okay, and it takes forever for the algorithm to converge, or might not even. And I mentioned why this method sometimes might be slow. So Levenberg and Marquardt did this smart thing. They said, why don't we combine these two into one formula? How? We simply, if you look here, this method has simply a number times the gradient with a negative sign added to the current point. This point has inverse of Hessian times the gradient. So it says, let's just factor out this gradient. So it's going to be the constant number plus the Hessian matrix inverted. And this is what these two people do. They combine the two into this format. Hessian plus lambda times identity matrix. This identity matrix is the same size of the Hessian. If this is n by n, this I is also n by n. Invert it, and then what? Then go ahead and multiply it by the gradient, and this is going to be your update equation. So here, if this gain lambda goes to 0, so you choose a very small lambda, what does it mean? It means that this second term is almost 0, so you simply get what? You simply get the Newton-Raphson equation back, right? Which is here. If lambda is very large, goes to infinity, on the other hand, this lambda I will dominate the Hessian matrix, correct? And so this term is going to go to lambda times I, the whole thing inverse, right? That's what it is. When lambda is very large, the Hessian can be neglected in front of lambda I. And you know, this is going to be 1 over lambda I inverse, and I inverse is the same as I. So basically it's going to be, if you call this 1 over lambda whatever mu, let's say, it's going to be the same as what? It is going to be the same as this equation where this term here can be called mu. So for large lambdas, it is the gradient descent. For small lambdas, it is the Newton-Raphson method. And it's a mixture of the two. Now, what does this mixing give us, right? That's the major thing. This mixing gives us what? Well, let's take a look. So one of the problems we had with Newton-Raphson is it's amazing when you're close to the global minimum. If you're not close, what's going to happen? For example, as I mentioned, one case is this being far away, and let's say you are on a flat area where curvature also cannot help and gradient cannot help. Now here, although gradient cannot do a huge help and curvature cannot do a huge help, but between the two, gradients can help a little bit more than curvature. Because if the gradient is very, very small, curvature is almost 0, right? Just consider here, if you approximate a line search along it with being just like, if you cut this plateau with a vertical plane like this, and you get this line, if you plot that line, it looks like this, or let's say it looks like this, very, very small slope. So here, maybe gradient, which is the same as f prime, is a very small number, let's say something like 0.1. But what's f double prime? What's the curvature? Well, for a line, it's what? It's 0. And it means in this equation, you are dividing by 0, which is like this matrix is singular, so it is going to give you error. It is going to give you a hard time. So if there is a very shallow slope like that, the gradient method is going to be slow, but still works a little bit. Still can get you somewhere, although very slow. The Newton method can easily, completely fail. Okay? So while you're far away, especially on flat areas, this method will set the lambda to be very large, which means make it close to what? The gradient descent method, right? And of course with the small gain, because you're inverting that big lambda. So you're taking small steps, but gradually you will get downhill, and ultimately what? You get to somewhere that you can go down, right? Well, the Newton method completely fails. This method does help. On the other hand, if you are on close to the minimum, like this function, which is, this is another example we're going to see, it's called Rosenbrock function. This Rosenbrock, which is this kind of function, and the previous function, by the way, it's this ratio function. This is a hard function for optimization problem. It's a benchmark for optimization algorithms to see whether they are performing well or not. The problem is the minimum of this function is one single point at 1 and 1 for these two parameters of 1 and 100, which are typically used for testing the performance of an optimizer. And this global minimum is along this blue band, which is basically a what? It is a long, narrow, parabolic shape, flat valley. And this area as well, which is also quite flat, and then we have the narrow valley as well. Okay, so it looks kind of like this kind of profile. And the thing is, when you go with gradient descent, it takes forever for, if you start wherever you want, it takes a good time for this method to what? To converge, because as I said, the slope is very minimal and it takes a long time. While the curvature is not super bad necessarily here. This area is parabolic shaped. That's the thing here. If you look at the slice here, the slice here is not going to be a line. The slice is going to be a small, shallow parabola. And when your cost function is parabolic, that's where your Newton-Raphson method is the fastest. Because this Newton-Raphson method already implicitly assumes your function is parabolic. So if it happens to be a parabolic, then this function is amazing. This Newton-Raphson method convergence is amazing. It's very fast. It uses this curvature and makes it jumps very fast and get to the minimum. I'll show you in a MATLAB code in a minute. So when this method of gradient descent is just taking small baby steps and taking it forever, as long as you have some mild curvature, the Newton-Raphson is amazing. It does a very great job. Okay? And I told you, on the other hand, if you have kind of linear behavior like this, the Newton-Raphson would fail, especially when you are far away from the global, while the gradient descent would work relatively fine. So this method says, let's combine. How do we manage to change the gain gamma so that we can make one of these two methods, GD or NR, dominant? How do we do that? This is the overall approach of Levenberg-Marquardt algorithm, or LM algorithm. It says, here in each step, I use this update equation, and from my current point, I get my next point, right? Then I evaluate my cost function f at the next point and compare it to what? To the current point, correct? So here, this is the vector x. It has all variables in it. It's a vector. If it happens that it is what? Less than the previous one, which means I'm going downhill, correct? So my previous point was above my current point, and you're going downhill, which is the right direction, and you're doing your job right. What should you do? If you're going down and you're going the right direction, then we accept this update. In other words, we calculated the current point through this formula. We say that's a good point, let's keep it. And then, since it is showing me that this curvature information is helping, what do? I want to give it more room. Now that curvature is helping, let's give it more room. Let's basically raise the importance of it. So what should I do? I should bring lambda down, correct? So that's what I do. I bring lambda down by a factor of 10 or a big factor, typically order of magnitude. So again, if my function drops, which means I'm getting closer to the minimum, I accept the new point, which is acquired by this update equation, and I bring down my alpha to raise the importance of the curvature. So I give priority to the Newton-Raphson. You say, hey, Newton-Raphson, you lead the way. It seems like you are doing a good job. It seems like Hessian is leading us fast to the global minimum. If, on the other hand, what happens is my current point, the value of it turns out to be bigger than the previous point. Means I went uphill instead of downhill, my update was not good, then I'm not going to accept the new updates, right? So in other words, if, let's say here, let me show you on a picture, if this is my point f at xn, and here I go down to fxn plus 1, which is less than xn, I say good. I should take this motion, go from here to here, right? This is a good motion. On the other hand, if it happens that I'm here initially and now I go there, I go up, right? So my f at the new point is bigger than the previous one. I say, no, don't accept this motion. Go back to wherever you were. Don't do that. Go back and try to redo your update. How would you redo your update? The only thing you need to change in the update equation is the gain lambda. The update was not a good update, means the Hessian matrix was not helpful. So what should I do? I should bring down the weight of the Hessian and add to the weight of the gradient descent. So I should increase, make lambda go up. So in this case, we reject the optimizer, or we say we retract back and increase lambda by a factor of 10 or some big number. Why? Because if we make lambda big, what's going to happen? It means the gradient descent is going to be dominant, so it'll take over, and although slowly but surely move me downhill again. And the other thing is, that's probably the reason is because your H matrix is not positive definite. Remember, I told you, if your H matrix is not positive definite, the Newton-Raphson method is not going to lead you down the hill. So what am I doing here by increasing lambda? Well, in this update equation, when lambda gets big enough, ultimately, this whole matrix becomes what? Positive definite, correct? This whole matrix becomes positive definite, although Hessian itself is not, but for a significantly large lambda, this matrix becomes what? Positive definite, and then it will lead to the minimum, okay? So that's why we are increasing lambda if my update goes in the wrong direction. Good? So this is the whole logic behind LM. Whenever Hessian is working, give it more and more importance. Whenever the Hessian is not positive definite, it is taking you to the wrong direction. Go back, do not accept the update, and bring up lambda, so you hopefully make this whole matrix that is inverted, what? Positive definite, so now you can get to where you want. So in general, this LM algorithm, it is faster than the gradient descent. It is slower than Newton-Raphson method because it needs this going backward, forward, changing lambda, and so on. But it is more stable than Newton-Raphson. Remember, the problem with Newton-Raphson is it sometimes works amazingly, some other time fails so badly. The gradient descent is always working most of the time. You can show that it is easily working, or all the time it is working. The problem is sometimes it is so slow, it does not look at the curvature. So this method does a compromise. Say, hey, I bring the speed down a little bit. So in terms of speed, gradient descent is slower than Levenberg-Marquardt, and it is slower than Newton-Raphson. In terms of speed, correct? Let me write it somewhere else. So in terms of convergence speed, and then in terms of convergence stability or stability of convergence. So how far or reliability of the convergence? The LM algorithm is, as I said, faster than gradient descent, and it is slower than Newton-Raphson, but at the same time, it might not be as stable as GD. It is quiet actually, but it is definitely way more stable than Newton-Raphson, something like that. Okay, so that's the good thing of this method. With some compromise on the speed, it makes it very reliable, and that's why you use this, as I said, in nonlinear curve fitting. Use it in places that your functions are not nice smooth functions with single global minimum, everything is perfect. No, many cases your functions have so much irregularity, so much bumps, so much global minima, and so on, and optimization in those cases is not easy. One example, as I mentioned, is neural networks. When you are trying to update a neural network and update the gains in a neural network, your functions in a neural network are complicated functions, like convolution functions, like the ReLU function or rectified linear functions, and so on. So in neural networks, because the functions you are using are nonlinear, or even if they are linear, they are not completely continuous or smooth like these or other types of functions. Your surfaces that you're trying to find the global minima of are very complicated. And optimization in those cases is a challenge. That's why in many of those we use Levenberg-Marquardt instead of Newton-Raphson or instead of gradient descent. Now, I said tons of theory. Let me show you some action. So here I have two functions I want to show you. One is the Rosenbrock function, the function that is a challenge to the gradient descent. It takes a long time to converge, while Newton-Raphson does an amazing job on it. The other side is this ratio function, which is kind of like the MATLAB symbol, right? It has two global minimum and two global maximum. They are the same numbers, so it's symmetric. And this is the location of global min, and the center of this blue spot here, and the center of this other blue spot here is the other point. This Rosenbrock has only one global minimum at 1 and 1 for value of A of 1 and B of 100. For this guy, this bottom one, Newton-Raphson fails while gradient descent works fine. And I'll show you for both cases, the LM algorithm works very nicely. So let's look at the code. So here I have the two functions. I choose which function I want to test. Function 1 is the Rosenbrock. Function 2 is that 2 minimum to maximum function with exponential in the gradient. I might call it the MATLAB surface function. And here I have the code for gradient descent. I have the code for Newton-Raphson, and I have the code for Levenberg-Marquardt, and we're going to see the performance of each. So first, let's look at Rosenbrock. So here we set up the numbers and the function. By the way, how do I stop my optimizer? The maximum number of iterations here I allowed is 10,000 steps, and the threshold here you see 1 to times 10 to the negative 5. What is this one is used for? This is used to show when I should stop. So this is my optimizer. It's moving, 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 moving. When the distance between not the points but the value of the function at the 2 points is less than the threshold. So if this is point xn and this is point xn plus 1, when the value of the function, the difference between these 2 points, the absolute value of it is less than that 10 to the negative 5, I say my optimizer does not move anymore. It's get stuck. Either it has reached the minimum point and that's why it is not moving, or it's just got stuck and it doesn't matter how many iterations I move forward, it's not going to move. So this is the threshold in the absolute change in the value of the function I use as a stopping criterion. So as long as this change has not reached and I'm below 10,000 iterations, I let my algorithm move. So here, Rosenbrock gradient descent, right? And I show you animation. The red star is the global minimum. You see the contour plot of the function and you see what? The gradient descent. As you clearly see, it took 10,000 iterations and the gradient descent barely moved from this point to this point. It is going so slow that it takes it forever to do anything. Here, to show you more, I let it go 50,000 iterations, okay? I let it go a lot more iterations. See what happens. The same function, but a lot more iterations. Look. Here we go. You see? By the way, the gain that I chose is 0.02. You might say, well, bump up the gain, right? Bump up how much the step size is. Let's do that, fine. So here is the function. Here is with some big gain, bigger gain. That is definitely moving nicely. Now, here we go. That's that narrow valley that it is getting stuck at. You see? It is taking more and more and more iterations. 50,000 iterations, it does not move anymore. It's almost stuck, right? So here, to make it a little bit shorter for you, I'm going to make it back to that 10,000 iterations or 5,000 iterations, but use a bigger gain of 0.2. Yeah, maybe 0.02 is too small. So here, right? Let's see. So the black point is the optimizer. You see, it gets a relatively good motion, but now here, the gradient is so small, it barely moves. Although it is moving very, very marginally, but you don't see that. So it takes some good time, goes through all 5,000 iterations, and it never gets much closer to the global minimum. Right? You clearly see that it is taking a long time. So let me stop it here. And you see, I stopped it at about 4,000 iterations. That it did not move. I really do not need to go that much. Let me just stop at 2,000, just for the sake of seeing the path. 2,000 iterations this time. And so you see, it's clearly stuck after so much. The improvement is very, very marginal, and it takes forever for this method to, you see, that's your path. It takes forever for it to get anywhere. And here you see a lot of oscillation around the valley. Let me show you that. If you can see, I'm moving forward, but first of all, the amount of motion is very marginal, and I'm just jumping from this side of the valley to the other side and back. So if I go back to this picture, I might show you better. So here, this is where the global minimum is at 1 and 1. I guess it's somewhere like here. I start here and I go down, and then when I get to this valley, this is what's happening. I jump like this. but then I slow down here, and it takes forever for me to get there. Okay, so you see your gradient descent is completely stuck, and it might never ever converge. Now, on the other hand, let's take a look at what? Let's take a look at the Newton-Raphson method here, right? So the previous one did not work even in 5,000 iterations. Now look at Newton-Raphson. It jumps. Did you see the big jumps? Done. 7 iterations if you look at my loop counter. In 7 iterations, it's there. It's amazing, right? How fast this method can go. Now let's do the Levenberg-Marquardt. So here we go. This method, you see, clearly it is first doing gradient descent, and then, but you see the steps are way bigger than that, and now that the gradient descent gets stuck, this method is using some curvature at the same time, so it doesn't get stuck in that valley. Look, you see, still moving reasonably. Not as fast as Newton-Raphson, but it does move. And boom. You see, I got there. It took me 33 iterations instead of what? Instead of 7 iterations, but I could get there. Now, on the other hand, as I said, if we go with function number 2, the function with 2 global minima and 2 global maximum. The minimums are the same number, that's why it has 2 global minimums. Look what happens now. So here is where the gradient descent works really nice. Look. I guess the gain was too high, or maybe I got there already. No, I didn't. Let me use a smaller gain here. That's the problem with the steepest descent, right? You have to decide on the gain, right? Unless, again, the method is not the vanilla version, you have an algorithm to tell you how to adjust the gain. So here I go with the smaller gain. Let's see. Boom. Right? So you saw with the bigger gain and rushing it, the gradient descent did not work fine. With a smaller gain, it did amazing convergence. And if I look at my eye, let's see if I can find eye or something somewhere. Where is that? It took about 2,000 iterations, but because it really wanted to get there to very, very perfect threshold, because this threshold is what? So small, 10 to the negative 5. But it did work pretty nicely, right? Now I might be able to bump it up a little bit, and hopefully it is still working. So here, you see, let me do this one again with 0.1. Let's see if this one converges nicely. There we go. Now, when you want to really make it less than 10 to the negative 5, that's the problem. Right now, your gain is so small and your algorithm does stick to the same gain of 0.1. Okay, that's the bad thing. It works, but you really have to try different types of gains for the best performance, right? So here, but you see, it is converging there. Clearly, the direction of motion is where it should go. As you can see, there is an optimum gain value, which in the simple gradient descent, there is no way to tell unless you have the function, which is never happening in real life. On the other hand, if I apply now, look at Newton-Raphson to this algorithm, to this surface. Look. It goes the other way. It's on the flat surface, on the plateau. And now it goes so far that although it's just 8 iterations, but now the change in the function is what? Very, very marginal, and you're stuck. So it clearly gets stuck on somewhere here and definitely did not converge. You see, Newton-Raphson completely fails here. Now look at Levenberg-Marquardt here. You see, taking smaller steps, now it is accelerating because Newton-Raphson is taking over. And a little bit slower, but surely, even with some oscillations, this let you converge. So here you did some overshoot, but it's no big deal. I still could converge, right? Even if I overshoot it. So if I want to summarize why this method is such a great method, is because it combines the speed of Newton-Raphson with the stability of gradient descent, and it also has an automatic logic for updating the gain lambda, right? If the function drops, and your goal is to minimize, if your function drops, you reduce lambda by a factor of 10 and accept the update. If the function value goes up the wrong direction, you do not accept the update and increase the gain gamma by a factor of 10. Okay, so that's the beauty of this method. It's a little bit automatic, and it is also what? It is reliable yet reasonably fast. Okay, so hopefully this video was useful to you, and I will see you in my next lecture. Thank you.